Today's webinar from Texas Instruments 2021 webinar series is 10 Geometry Gems. It is also presented by Peter Fox. Hello, Peter.
Hello, Brian. How are you?
Very good, thank you. Wonderful, as always, to have you join us. You've just been running me through a short preview of what's in store. I really like what you have there for us. That's enough from me. I'm going to switch us across to Peter, who will then run us through the clever ideas that he's just been showing me. Thank you, Peter.
Thank you, Brian. Okay, so there's only 6 little tips that you can see on the screen, but some of those little objects, if you like, or some of these little tasks have multiple little gems that you're going to encounter. They range in difficulty and range in year level, anything from year 7 through to year 12. And when I say year 12, all the way through to year 12 specialist maths if you want it to. So I think we'll start with something simple, and by all means with some of these simpler ones, feel free to follow along. I'll put up the process that we're going to use and you can have a quick shot on your software, because don't forget the event's being recorded, so therefore you'll be able to watch it back and catch up on things that perhaps you couldn't follow at the time. Or if you see a nice little tip along the way, then quickly jump off, try it, and then come back. But let's start off with this thing that I've called Constraint Geometry. So it's the idea that we can lock functionality of objects in the geometry space. So here's the steps that we're going through for this one. We're going to start by just drawing a triangle using the Shapes tool, pretty easy. And then we're going to measure its area, and there's multiple ways you can do that. Then we're going to lock the area, and then finally explore how the vertices of the triangle can move when the area is locked. So that's our 4 steps. So as I said, starting off pretty easy. So I'm going to go over to my software. I'm going to start a new document, and I'll do this one in the geometry application. And that might sound stupid, but we will actually use the graphs and geometry application later on, which is now just titled graphs application, but originally it was graphs and geometry. So we start by menu, shapes, triangle, we said, and our cursor changes to a pen. Students are fairly familiar with this sort of a thing where they get a pen to draw, so it's fairly intuitive that we'll click and create 3 points. So I've got my triangle. The next step was I said I was going to measure it. Now, if I hover over the object, it tells me it's a triangle. It's pretty clever. And then if I hit the right mouse button, I'm using my computer at the moment, students would press Control Menu and choose Measurement and Area. It's not the only way we can arrive at that menu. If kids prefer to use the menus on the keypad, they can press Menu, Measurement, and then Area, and then click on the triangle. Okay, so once I've done that, I can just drag the vertex around and see that the measurement changes. Oh, that's fairly handy. I like that. I'm going to stop on that one. And then the last step, or the third step rather, was to lock the area. You can see it's even got centimeters squared. So I'm going to right click, and again on the calculator, kids would press Control and Menu while they're hovering over the measurement. And under Attributes, this is where we choose to lock something. The first option we see in that little drop-down list is the precision, how many value or how many digits we want to display, and then you use the keypad to arrow down, and it says currently the object is unlocked. If I arrow to the right, it will be locked. So now the area of the triangle is locked, it cannot be changed. And this is not the only triangle in the world with an area of 100 square centimeters. But the question is, what happens if I move this vertex? I can't move it up or down, but I can move it from left to right. And this is something that the reason why I do this with dynamic geometry is the fact that that's not something you can do with a pen and paper. Not easily anyway. So I can see that it moves kind of horizontal. If I want to track where it's moving, then I can go Menu, Trace, Geometry Trace. Click on the vertex that you want to track and then just drag it, and it will leave a nice little trail behind. So it would seem that our triangle, if it's got the area locked, that the vertex moves in a straight line and what appears to be a straight line parallel to the base. I can just, now this is not a proof, of course, but if I construct a parallel line passing through that point, whoops, that was a perpendicular one I chose, try that again, construct parallel through that point and the base. It's like, well, where's the line gone? Can I get rid of the trace? Of course you can. Menu, trace, and now erase trace is an option. So we can see that this point moves parallel to the base of the triangle. So the things that are changing is this length here and this one here. The base is constant. And of course, we could say that the height of our triangle is constant. And we could put some extra constructions in there, but we've got a lot of other tips to get through. So that's what happens when we use what's called constraint geometry, and you're able to lock things. All right. This one's got locking and unlocking involved. So the one we just looked at was suitable really to students in Year 7 and perhaps Year 8. There's some activities on our website which do exactly what you've seen on there, but also include parallelograms, and we look at how parallelograms hold a clue as to how the area of a triangle might be calculated as well. But let's have a look at one that might be, using the same concept, applicable to students in specialist maths. So this time we're going to put the triangle in the graphs application and lock the perimeter. And people might like to put in the chat what path the vertex might follow if the perimeter of our triangle is locked. All right, so it's the same sort of thing as what we did before. We're going to draw a triangle, but in the graphs application. This time measure the perimeter, not the area. We'll lock the perimeter, drag the vertex, and then try and determine an equation. And for that, I'll let people put it in the chat. I'll try and make the equation, let's say, relatively straightforward. We'll see how we go. So let's go back to our software. I'm going to use the same document. So I'll just do Control-I and I'll insert my graph application. Now, the other thing I'm going to do here to make it a bit easier for me to place the point, I'm just going to add a background in here, what we call the grid. We're going to use that a couple of times just so we can see, it's a grid. So let's draw our triangle. So when we go in here, you'll see our geometry functionality still sits down here. We've just got an extra layer of menus to get to it. So shapes and triangle. Now, I could put them up here, but I said I was going to produce an easy one. But if you wanted to precisely locate the object or the curve that we're going to do, then that's the advantage of having the grid, is you can lock in integer values fairly easily. I'm going to put it on the x-axis. Let's do it at 2 and 1, 2, 3, 4 will do. And then just out here. Now, here's where you've got to be careful. If you've got that grid in the background, make sure you don't land it on. If I do it near a point on the grid, you'll see it says point on. I don't want it on the grid. I want it near it. That'll do. So now I've got a triangle that I can move around however I like. And I'm going to measure the perimeter. So menu, geometry, I could have right-clicked measurement just to show you these things. And this time measure length. Now the cool part is I don't have to measure each side separately. It's measuring the perimeter. If I wanted to measure length, I'd click there and then there. So I'd click on respective vertices. But the perimeter, it is by default the length that it's measuring. You'll notice also it says 16 units as opposed to centimeters, because we can change the scale on these things and we're not really talking about centimeters. They're arbitrary units. So at the moment it's about 16. I could right click on that, look at the attributes and see how many decimal places I'm going to display, move that around. I haven't locked it at this stage. Let's make it about 16, shall we? That's pretty close. But from now on, I'm going to lock the perimeter. So remember, that's under attributes. And you see I get exactly the same scenario that I had before. And I'm just going across. The perimeter of this shape is now locked. And I'm going to move this vertex. I'll label it. I'll call it A. I've got point labeling turned off, by the way. You might have it on, in which case every time you create a shape, it's going to label the vertices. Now, Brian, I'll get them. Has anyone put in the chat what equation might map the path of our vertex A if I move it around?
There was a fellow by the name of Neil who suggests we're going to end up with an ellipse.
An ellipse. I think Neil's pretty cluey. So let's try it. If I drag it, I can't drag it up very easily. I can kind of drag it down. It jumps on me. But I think Neil's right. Look at that. It's beautiful, isn't it? And I can do exactly as I did before and go trace. Now you'll see there's a whole lot of other trace options. I haven't got a graph that I'm going to trace, but I'm doing the geometry one as well. And I'm just going to click on that vertex. And there it is. Now, if I was doing specialist mathematics, I might come up with the equation parametrically, which we'll have a look at in a minute. Or I could do it using complex numbers. So I know, for example, the total perimeter is 16, and that this distance between here and here, now at the moment I've got to count the little tabs, but if I jump out of here, let's see if I can get the axes to display. One of the attributes they've now got on the axes is to display all tick marks. That makes it a bit easier for me to figure out. So it goes from 6 all the way through down to -4, but across here, this distance here is 6. So therefore, the length from, let's label the vertex so I can refer to them easier. Label. So distance AB plus distance AC must equal 10. So if Z was a complex number X plus YI, then I'm looking at the distance from, let's say, whereabouts are we, -2, plus the absolute value of Z to 4, that total distance has to equal 10. That would be my equation for the ellipse. Now, of course, now I'd have to find Z is equal to X plus YI and then work it all out, come up with a Cartesian equation for that. Or we could do it parametrically. Now, if we're doing it parametrically, let's change that. Have we got anyone, Brian, game enough to suggest a function for X of t? I'm going to start off like that.
It's looking quiet at the moment.
I'm just going to take a quick stab in the dark at that one. And I'm going to think it's somewhere, and this is just approximate. But it looks pretty good, right? I'd have to double check that by doing a little bit of trigonometry, but I did choose these numbers so that they would work out nicely, right? So there's our parametric equation. I think it's kind of nice, but I do like the complex numbers approach that we can talk about the sum of the distances as being constant and getting the equation that way. And both, obviously, the parametric and the complex numbers equation work quite nicely. So that's our first couple of tips. You were going to say something, Brian?
I'm just agreeing. Yes, indeed. I like the bringing together of those different representations.
That's it, and both based on this idea of constraint geometry where you can lock a variable. And remember that you can do the geometry in the graphs application as well. All right, let's have a look at linking variables. Now, this is one I've done as an interactive. So we don't always do it so that the students do the construction. Sometimes it's useful to have them do a construction. Other times we want to create some sort of an interactive environment for the students to work in. So this is one where we actually link variables, and it's something we're going to use in other constructions, so I thought I'd cover it now. So let's have a look. For this one, I think I'll start a new document. I'll ditch that one. I'll start a new document. And again, we're just working in the geometry application. And I want to draw a horizontal line. Now, there's a couple of ways we can do it. There's a really quick way in the computer software. So I'm going to draw a line. And the other thing that's nice about using this stuff, if the kids are doing it or the students, is that they start to learn what's the difference between a line, a segment, a ray, a tangent, etc. So I'm going to use a line. Now I'm going to hold down the Shift key. So I've got the Shift key held down, and you can see that the point sort of jumps around now. But now as I hold the Shift key down, see how easy it is to pull out a horizontal line? And if I move down, it's jumping in steps. So it's a good way of just creating a horizontal line. Then what I'm going to do is create a line segment, but I want to make the line segment a specific length. So let's make it, oh, I should show people how to get to that too. So either right click for text or menu, actions and text. And I'm going to just click in there and type 24. So my line that I want to create, my line segment, I want to create it as 24 units long. Now I could start it there. Let's do that. There's reasons why you may or may not want to do. Actually, I will. I'll start it somewhere else. You'll see why. So I'm going to just put another point on that line. And now I'm going to use the circle tool. You can use a compass that will do the same thing, but has a different reason for its use. And now notice, rather than having to drop it anywhere, I'll point to the number 24. So now I know that the radius of my circle is 24 units long. I'm going to draw a segment in there from there, and you'll see automatically it jumps to that intersection point, and it recognizes it and goes intersection point. Now, important thing is I want to start hiding stuff. So if I right click, I can hide the line and hide that point. And I'm going to hide the circle. And I don't even need the 24. I can hide that as well. Now, why would I create this segment and not go through the original point? That's because, notice now as I move it, the whole thing moves as one. I can't move it up or down because the point was created on the original line. And because I've hidden the line, you can't move it because you can't grab the line. It's missing. It's hidden. Mind you, it's hidden, not deleted. Next thing I want to do is create a point on our segment. Now, I can go back through the menus, but on CX2 or the premium software as well, just press P, and then you can put a point on the segment. So now I'll measure that length, measure length from there to there, and I'll just leave that there, and I'll measure length from there to there, which doesn't look quite right at the moment, but that's because of the way it's rounding, how many decimal places we're displaying. So let's try that. That's not too bad. I might change that a little bit. It's better. Now you can choose how many decimal places you want displayed here. And the other thing I want to do is perhaps make it a bit more obvious which one is which in terms of I'm going to draw another segment and one from there to there. And that's just so that I can color them. You can right click. See, it also says tab because there's more than one thing in there. I'm going to make that one thick and I'll change its color. And down this end, I'll do the same sort of thing. Change the attributes, make it thick, and change its color. Now, I said this part was about storing or linking variables. So I don't normally put things in X because X is a variable and I want to use it for graphs, but for now I'm going to do that. I right click on the measurement and hit store. And you can see it's waiting and it says variable. Variable is assigned equal to, so I'll put X right there. And over here, I'll store that in Y. So the value of X is now 6.74 and changing, and Y is whatever that is as it changes. Now I'm going to split my screen. And down the bottom here, I'm going to put a notes application in, and I'll put an instruction to students. Write an equation relating X and Y. And we'll put a little math box in there. So now the student grabs this and moves it along. And if you really want to be nasty, then you give them one where, say, X and Y are pretty much exactly the same. And of course, the kids will write something like X equals Y. It's a little bit harder when they're this precise. So let's imagine the kid or the student writes X plus Y equals 24. It says true. In fact, it seems to always be true. What if the student wrote 24 minus Y equals X? Well, that's true and is always true. Oh, there's a false there. It depends on how well it's rounding, right? I'll tell you some tricks on how to round it later on. And of course, we could have written 24 minus X minus Y equals 0. So students can come up with their own expression as long as it's always true. Please ignore the little falses that flash up. But what if the student says, I think X equals Y? Because I've got to show you one where it is just false all the time. So what it's doing is using the values that we stored or linked in here, and it's using them in another application. And in this case, it's just checking, is that statement true or false? So it's a nice way to create an interactive environment for students to type in an equation and see if this variable that we've got and make some relationship between those variables. This is very similar to the idea of, when you start doing a rectangle with fixed perimeter and you're trying to work out the length and the width in terms of X and so on. It's the same concept. So that's how you store variables or link variables. And that's what you can see happening down here. You can see on the one that I've created, what I've done is I've rounded these numbers off so that they're only displaying integers. It's a bit more work when you create one decimal place, but look, it depends on the year level that you're working with. Some kids would much rather just see the integer values, and that's not such a bad thing, keeping it simple. So you can make it so it's always saying true by locking them into whole number amounts. So that's the process we went through there. All right, dynamic visuals. Do we have any questions there, Brian? I'm sort of motoring on ahead, but haven't stopped to check the chat.
Yeah, mate, we have, but I'm answering it in the chat.
Oh, okay, good.
So just wondering how you did the split screen, which of course happened very quickly with the software that you're using.
Yeah, I can show that on there. Yeah, that's not a bad one.
On the handheld, of course, we go through document and then
yes, that's right. Later. So yep. As Brian's just explained, I had a geometry application there, and if I hit the document screen and go down to option number 5, page layout, you can see that I can select a page layout. And I just chose option 3. There's a custom one which allows you to change the amount of space, real estate taken up by each one. But I chose layout 3. So I had, and the other thing too, a nice little tip, is when you've got two applications running, so I've got geometry up there and I've got, let's say I had notes down here. On a computer keyboard, I'll hold down the Alt key and press Tab. Well, there's no Alt key over here, but you can press Control Tab, and that shifts the focus between the two applications. So if you know Windows is Alt Tab, on the calculator, it's Control Tab. So that's kind of cool. We kind of kept that as close to what you might be familiar with. All right, so this new one, I'm going to put another geometry application in. And let's have a look at the actual problem. In this case, I want to create an interactive environment. So this is something that we as a teacher would be creating for students to use. So let's have a look at the mathematics around the problem, and I'll get viewers to perhaps suggest an equation, and we'll see if their equation is correct. I'll pause my speaking when we get to that point. So we've got a rectangle that's been circumscribed by a triangle. That means basically we've got a triangle that's touching each of the vertices of the square. The base of the triangle is 3 centimeters longer than the rectangle, as you can see in the diagram. And the height of the triangle is 4 centimeters more than the height of the rectangle. And this is something that's staying constant. And what we want to know is the minimum area of such a triangle. Now, if you give this problem to students to determine the minimum area of the triangle ABC, it's actually quite challenging. There's a few little tricks that they need to know. But the other thing is then they'll do maybe some calculus, let's say, and they're not sure. So they'll turn to the back of the book to see if they're correct. But here, and this is where the dynamic visuals come in, we don't need the back of the textbook. So let's get this underway. So I would like to construct a triangle first, but I've got a whole lot of conditions on that triangle that I need to meet. Now I know that I need to create a length of 3, but we did that before. I just put some text in there and said 3. There's another length which I need to create, which was 4. So I'll put both those measurements in there for now. I'm going to use those later. Notice also that you can change the scale up here, and that will make your diagram bigger or smaller depending on, you just click on it and change it to whatever you need it to be. So if you want to do something, say, that fits an A4 piece of paper, you can change the scale so it can be 29 centimeters by 21 centimeters, 29.7, whatever it is. So I'm going to create a line that holds the base of my triangle. Same tip as before. I'm pressing the shift button. It's going to give me a nice horizontal line. I'm going to put a point on that line. So I'm going to go through the menu this time rather than just pressing P. And here's the tricky part. I want to create another point that represents, let's just go back to the diagram, this length X. So if I just put another point on the line here, it could go in both directions, and I don't want my diagram to do that. So I'm going to use a ray this time. So my ray is going to go in that direction. So I'm going to start hiding this line. Now remember, I just did that so that students can't grab that point and move it up and down and muck the diagram around. But they can move it that way. That's fine. You can also, if you want to, here's another little tip, is pin that. And now it's locked. You can see it says pin and you can't move it. It's pinned to it. I'll hide that one as well. I can still grab the screen and move it, which you can also stop, by the way. Just right click on the screen and pin the screen. Now I can't grab the screen either, and I can't grab that point. So I've now created something that is quite useful. Now, if I construct my point on this ray, that's, if you like, my distance X. And now I need to create something that's 3 units beyond that, because it tells me that the base of the triangle is 3 centimeters longer than what this X thing is. So we sort of did something like that before. We had a circle, and I'll make it 3 units long. And now I need to put a point. It's an intersection point. Or if I'm just going to choose point, and notice as I move it, it tells me this is an intersection point, and that's good. I can hide the circle now. And now if I move this along, you can see that it stays this fixed length. I can now hide this ray as well, and hide that wandering point out there. And now I've got this thing going along here. So I'll put my little segment back in from here to here. Now the hard part, I've got to create this one up here. So I know it's a vertical line, so I'll construct it perpendicular. So my triangle needs to come up here. Now, here's the trick. If you have a look back at the diagram, you can do some similar triangles. And in the original problem, it says, well, first of all, you've got to show that x times y is constant. Well, it turns out x times y is equal to 12. And you can do that from similar triangles, because this triangle here and this triangle here are similar. We've got an angle here which is the same, being a right angle, and we can show that that angle and that angle are the same, and that one are the same. And if we've got similar triangles, we can use ratios. X times y equals 12. So I'll put some text here, and this is another little trick. I'm going to have 12 divided by some length. I'm not going to say x, I'm going to put a, because I don't like using x's and locking it out for use anywhere else. So what does that do? Well, I'm going to calculate it. So I'll right click on and calculate, and I'm going to, oh, I haven't done my measurement yet. My mistake. Menu, measure the length from here to here, my length x. Right. So now if I right click on there and say calculate, it says, where's your value for a? Or in other words, my x. Well, it's right there. So now if I do another little circle, starting there, of that size, that's pretty small, isn't it? But watch what happens. Neat, isn't it? So now that's that length that I want. That's my y in the actual diagram. And now I need to create a distance 4 centimeters above that. So I'll do shape, circle. I need the center at there, and then 4 centimeters. And now I'm ready to do my triangle. It goes from that point to that point to that point. There's my triangle. I need to draw in my rectangle, so I'll drop in some perpendicular lines. And now I need to draw a rectangle, but another little trick in the geometry application, it's very difficult to make a rectangle that's defined by 4 points. I know that's really weird, because the software or any dynamic environment doesn't know it's always going to be a rectangle. So in actual fact, we know it's going to be a rectangle. So I use a polygon tool. And for a polygon, because you could have as many sides as you want, you click on the first one, the second one, the third one, the fourth one, and then go back to the first one to finish it off. So I know it's always going to be a rectangle by the way it's been constructed. I'm going to fill that in with a, we'll do blue because that was what was in our diagram. Now I can hide a lot of stuff. So I'll hide that line. I'll hide that circle. Now, another way to do that is if you do actions, hide and show, you can then just go around and click on stuff and hide lots of things at once. Now, I need that point, but probably don't want that point. Now, if I try and drag that, it's like, oh, well, what happened? Well, you can't drag that point because this is a 1. So to help students, I normally label it. So I'll label it something like P. So I'll say to them something like drag point P. And now we go, oh, I wish I'd drawn that bigger. Well, you can. See, I just changed the scale up here. And now I can make it bigger or smaller. And this distance here is always 4. We can check that. Measure length from here to here. And from here to here. And from here to here. And I can drag my point P along, and we see that the base of our triangle is this length here plus 3, and the height is this length here plus 4, and so on. And I want to find the minimum area of this triangle. Well, I need to sort of find out what the area of the triangle is. Well, we did that before. Right click, measure, area. And now as I change it, I don't think that's measuring that triangle. Let's just get rid of that one. Delete, measure, area. There we go. So I wonder where the smallest measurement is. So you can either keep watching to see how you capture these variables, or you can try and figure out an algebraic expression for it. I've got a couple of minutes that people can do that with. I'm going to show you how you can actually start capturing these measurements. This is the next part. So we've kind of done this interactive environment, but I'm going to show you data collection. And to save time, I'm going to use the same diagram, the same thing that we're doing before, as in with our same interactive, our manipulative. So we're using a triangle. We need to measure the base of the rectangle. Well, I've got that done. We need to measure the area of the triangle. Well, I've done that. And we want to capture both sets of measurements. So let's see how we do that. There's our base. So the first thing we do is right click on it and store it. And I'm going to call that rectangle base, RB. And I'm going to store this one in rectangle area. And I might hide these other values too. Don't delete them, because if you delete them, the whole thing will come undone. So we'll just hide some of them. It's kind of annoying that the hide and the delete are right next to each other, isn't it? That's probably why the hide show is a better option, particularly if you're using a calculator. Might hide that measurement for now as well. So what we want to do is have a look at this length here and this area. So as I change it, I can see that that's changing the area of our triangle. And don't be worried, it's actually or storing more decimal places than that. So I'm going to insert a spreadsheet. And on the spreadsheet, I'm going to have base and area. So these are the names of my lists, not the names of the variables, but the names of my list. And I want to capture the variables and store them in this list. So menu, data, data capture, automatic, and here we call that rectangle base. I could also hit the variable button and it would tell me as well. I'll do that on this next one. So menu, data, data capture, automatic, and press the variable key. And the one I wanted is rectangle area. So what? So now if I grab that and move it, doesn't matter if it's gone all the way up the screen, it's recorded all that information. So now we could put in a graph application and let's do a scatter plot. And we've got base and area. Now we'll just do a zoom data. So there's a minimum down here somewhere. And I'll leave it to the viewers, Brian. Has anyone typed in an equation? Probably not. There's a lot in there to see if they can come up with what might be the function. And the idea is when students type in the equation or the function that fits this, then it passes through all of our points.
Haven't got one there at the moment, Peter. Looking at some sort of hyperbola.
Well, it's actually a mixture. It's got some, I think there's an x squared in there from memory and some sort of rational something over x. It's to do with the fact that we have similar triangles, which, by the way, we're going to have a look at some translation stuff later on, but let me do it here. I've got a shape down here, a triangle here, 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 and here. Oops. And let's just color that triangle in. So this triangle and this triangle are similar, and we can sort of show that. I'm going to drop a vector in. Go from here to here. So then we can put a translation in. We can say, let's translate this triangle using that vector. And there it is there. We can also dilate it. Now we'd need to do some sort of a calculation for the dilation, but we can dilate that and show that it fits nicely into this triangle up here. So that's your translation tool. Let's get rid of that one. So I'll leave that one for now. I'll leave that one up for the the viewers to figure out what the relationship is. By the way, it's already an activity up on our website, so the answers are in the teacher notes, which you'll get all of the information linked from the PowerPoint slides anyway. There's a couple of other ones. This next one I'm still working on the document, so that one will be up hopefully later on this week, and it's the last one that we'll have time to cover. So let's go back in here. Bezier curves. These are really cool, really cool. If you got some time later on, just when you finish the webinar, check out Pixar in a box. So we're going to do some computer animation as they do at Pixar Studios. If you're wondering how they do the animation of the hair on animals or blades of grass and all sorts of plants, they actually use mathematics. And in this case, they use Bezier curves, which is so cool. So gives you an excuse to watch Shrek or something like that in class and say, we're doing maths. So let's check it out. How do we do it? All right, I'll start a new document. You might be able to see I've got it already down there, but I'm going to start a new one just so everybody sees the whole thing. So you had something there, Brian?
Yeah, I was just when you mentioned that you'd published that activity, I was just going to put the link in. Now I'm assuming you've got it under the special maths.
Year 11. No, that one for the triangle, calculating the maximum or the minimum area. It's in Year 11 calculus for Victoria. And by the way, folks, the answer is when that's 3, that's when we actually get the minimum area. And it's because this here is a 3, 4, 5 triangle, and so is this one. So these triangles are actually exactly the same. They're congruent. That's when the minimum area. So you might even like to think, why does that happen? Why does it happen? The minimum area is when these two triangles are congruent. It's kind of a cool aside.
So you got it in the methods course. I'll put the link into the chat now, Peter.
All right, beautiful. Thank you. All right, so again, I'm just going to put the grid on the background here. And I'm going to put 3 points in. I'm going to use my keyboard this time. Just press P, point. Some astute viewers might have seen there's also point by coordinates, and that's kind of cool. You can define a point now by coordinates or by a rule. So you can set your point so that it follows a specific rule. So as students drag it around, the point will only go where it satisfies the rule. And that's pretty clever. All right, actually, I might move that down there. And let's move that one over there. That's it. Now, I've just moved them around so that people will perhaps recognize the first part of this activity. It stems from Year 9 all the way through again to Year 12 Specialist. But let's just start by putting some line segments in. One going from here to here, A to B and B to C. And I could put them so that they land on the grid, but I want to be a bit more flexible than that. So I'm going to add in some midpoints. So midpoint from here to here. Then I'm just going to repeat that process a couple of times. And I'll do the same along here. So I just keep on clicking and it just keeps putting midpoints between successive points. Making sure I do the same quantity of midpoints on either one, and I'm done. And then what I'm going to do is add in some new line segments. So let's go measure segments. There we go. From there to there, 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 and there, and there, and there. Job done. Now I can drag it around. And this, what we call an envelope here, is the curve for which we are seeking. I suggest that because of the way this has been produced, that is a quadratic. Now I could go ahead and just type in x squared like that, and then just move that and try and fit it in nicely and say, yeah, it's pretty close. because this doesn't prove it at all. This is just, well, it looks like one. And people that have been to any of my workshops before, they know I don't like just it's a parabola because it looks like one, because it's a U-shaped curve. There's got to be some reasoning behind this, and there is. So that's one way to create this curve. And there's a whole series of activities on string graphs that you can follow along that uses Cartesian geometry, if you like, or coordinate geometry. But I'm going to do this a slightly different way. Let's put our grid back on. And I'll put a little segment in. Where are we? Points, line, segment. That'll go from here to here. And then I'm going to put a point on that segment. And now I'm going to measure some lengths. So we'll go menu, measure length. We'll measure the length of the line. Up there. And that one. Up there. And now we're starting to combine all of the things that we've been doing so far. I want to use this little pretend slider that I've created to create a number between 0 and 1, a ratio as it were. So that divided by that. So we'll add some text in and do A divided by B. And now if I calculate that, that's A. Notice it's saying, where's A? It's like where's Wally, but easier. There it is. And that's the ratio that I want, anywhere between 0 and 1. All good. And now I'm going to put some points on the screen again. I'll put one in quadrant 1, I'll put another one in quadrant 4, and one in quadrant 3. And again, I could have labeling on, but I find that it crowds the screen a little bit. So I said about translations before, and you saw I used the vector. This term dilation, some kids don't like dilation towards and dilation away. I think it's because of the way it's taught and the fact that it's often only introduced more towards the senior end. Here's a lovely way to drop it into, say, year 10. So transformation, dilation. So I'm going to dilate that point in that direction by that quantity. And I'm going to do the same to this one. I'm going to dilate it from there in that direction by that quantity. Then I'm going to do the same with this one and this one by that quantity. Now as I move this along, you'll see they all move based on the ratio. Now to help viewers out, let me just drop some segments in, which I'll get rid of in a moment. From there to there, there to there, there to there. And hopefully you'll see that perhaps the thing that we've created is a little bit like what we had before. I'll do it as a locus, as that moves along there. So we can see the same sort of thing as what we had before, only we've got a lot more lines now. But I'm not actually interested in that part of it. And I might change these a little bit. And I'm going to change their attributes to turn them into dotted lines because I'm not quite so fussed about them. And I'm interested in how that point is traveling. So let's go back and do our locus again, construct locus. As that point moves along the line, let's track that there. Now that's kind of cool. Our locus is updating. Let me put that one there, about there. Let's shift that out the way. We'll put that one about there. Ooh, now it looks like a parabola. Let's check this out. Looks like y equals x squared pretty accurately there. That's cool. But let me just do something else. I said you could do this with specialist maths, right? So let's get the coordinates of that one. We'll get the coordinates of that one. And we'll get the coordinates of that point. And let's start storing them. I'll store this one in AX. I'll store this one in AY, and let's store that one in BX, and we'll store this one in BY, and more CX, and store in CY. So my quadratic was nice because of the symmetry that we had going on there, because I chose these specific points. But is it always a parabola? Well, I did it with a function. What if I did it parametrically? I'm not sure how many punters have seen this one before, but let's see how good my memory is. 1 minus t, I think it's all squared. Hopefully there's someone watching that will tell me if I screw this up. Now I think it's ax plus, and from memory it's 2 times t times 1 minus t, oops, times one of my other points. I'll say bx plus t squared times cx. Now I'm going to copy all of that, because this thing is symmetrical. I'll paste it in here, but I need to use AY, BY, and CY, and we just want to go from 0 to 1 in steps of 0.1. Oh, look at that. Now we've got a parametric equation, and does it always work? How do I know that's not my locus? Because if I put my cursor over it, it says that's my equation. So now you have a parametric equation that is modeling our Bezier curve. And I think that's kind of cool. And because you've got a parametric equation for it now, then you could write it as a Cartesian equation and have it as a general Cartesian equation. And I think that's just about all we've got time for, Brian. I hope people like that very last one. It kind of combined a lot of what we're doing.
That's the thing.
Transformations.
Yeah, very clever the way it brings all the ideas together, including, as I said, the various algebraic representations through the different systems, whether you're using parametric.
It's kind of cool the way that there's a bit of a clue here. Let me just change that tangent line. I'll make it red, and we'll make it solid so people can see it a bit easier. Oops.
Yeah, and of course the use of colour really helps with this.
That's it. And probably the only other thing which I haven't shown here, one more thing, might as well. If they're still watching, they're still on board with us. I'm going to insert a slider, and I'll call this slider show, and I'll say it can have a value of 0 or 1, and I'll make it small.
To switch them on or off effectively.
Correct. So I don't want some of these construction lines in, let's say. So I go down to conditions, show it when show equals 1. And we'll do the same for this one over here. Conditions, show equals 1. And if I was super smart, I'd copy that. And maybe this segment here, conditions, and maybe that point. And that point, only one more to go after this. So now you can hide them all at once. And we can hide all this other construction stuff if we want. We don't need it. And we end up with something that's just a nice, neat little diagram. And at any point, we can have the students just show some of the construction stuff that might be relevant.
Yeah. And of course, with a lot of this, it's always easier to build these things on the software and then transfer through to the handhelds.
Oh, absolutely. Yeah.
Yeah. And a reminder again to the participants that a lot of the material Peter has here will be shared afterwards when you receive your certificate of attendance, and links through to support materials to download. Meanwhile, I have put into the chat, I hope you've been keeping an eye on that, some of the links there, even if you file back through the chat, some of the links to activities, the mention of the string activities, which are published on the website for year 10. Obviously, Peter's taken it a lot further there, but also the triangle areas, which is in the senior curriculum inspirations, maths methods calculus. Yeah, so some terrific ideas there, Peter, and I can see we're getting some thanks coming in through the chat. I'll transfer back to my screen now.
Well, thank you, Brian, and I'll
just
check through with any other questions. Or did you manage to score them all?
I'll share my screen, and Pete, now's the time to type the questions directly to Peter. I did put in the chat a reminder that next up in our webinar program in 2 weeks' time, we have a session that's on music, linking music to mathematics, with the suggestion that music is really just mathematics anyway, but it's mathematics with feeling. And so if that's an area of interest to you or your students, please join us in 2 weeks' time for that. Meanwhile, certainly, once again, we'll thank Peter for the clever ideas he shared expertly with us this afternoon.
Now, just before you do go, Brian, I don't know whether you saw the one on TI-Innovator that I shared just recently.
I did. The Innovator Choir. How
the
very
Innovator
clever.
Choir, that's it. I'm just seeing if I can find the link to it. Not that one. Just bear with me for 1 second, because I think this is pretty cool. There's someone that's controlling a drone using a calculator. That's pretty cool. And there's also this other one using TI-Innovator. I think it's a lovely segue. I can't see the link to it at the moment. On getting a whole lot of TI innovators to play some music.
I tell you what, if you check your email, you sent it to me just yesterday.
Oh yes, I did too. All right, let me see if I've got it here.
Yeah, and it looks like one of these choirs of the a screen full of, looks like a Zoom meeting in the choir, which you've seen a little bit of that sort of thing.
So I'll put it in the chat to everyone now.
Yeah,
they can listen to that instead of listening to us. It's a whole bunch of TI innovators. It's in the chat now. It's a YouTube link. Someone thought that'd be clever. I think it'd be a great thing for teachers to do while kids are in lockdown. Collecting all their videos as they upload them and then combine them into the orchestra. I think it's an orchestra rather than a choir, but maybe it's a good segue into next week's session, Brian.
Yes, the Firefly. Yeah, very clever.
Yeah, links in the check it out, folks. You'll either love it or you'll hate it.
Just on that, a reminder that launching this week also was the TI Codes competition. So if that's something that you and your students may be interested in, we encourage you to go to the website. It's one of the first things that pops up on the TI Australia website, the information for how to enter this year's codes competition, and some pretty big prizes there too, Peter. I know winning schools will be receiving calculators, TI Innovator Hubs, TI Rovers, as well as, of course, medals. We've got to have medals. And certificates there will be. Speaking of which, of course, for your attendance this afternoon, you will receive a follow-up email to some of the files that Peter's sharing with you, and a link where you can go to the certificate and print off your certificate of attendance with your name on that. Yes, this event was recorded. If you'd like to see it again and perhaps play it back slowly and taking notes, all of our webinars are available to review on demand from the website at the same place where you registered for this event. And the other one, of course, is that they're also uploaded to YouTube. Look for our YouTube channel and please subscribe to that to ensure that you do remain up to date with the various services and products that are available, I strongly suggest you register for the newsletter. And any further questions, phone the office directly. So with that all done, once again, I say thank you to all our participants, and of course a special thank you to our presenter this evening, Mr. Peter Fox.
Thanks, Brian, and hopefully we'll catch up with everyone face to face on our Snap opening when that happens.
We all look forward to that, Peter. Yes. All the very best. Good evening.
Thank you.
Okay.